Good morning, ladies and gentlemen. It's a real pleasure to be here today. This is our 11th lecture in our WISE Public Lecture Series, and we're delighted that you're all here today. The Waterloo Institute for Sustainable Energy was formed approximately 5 years ago, and our vision is clean energy, accessible and affordable for all. And we have over 95 faculty members and hundreds of graduate students within our institute. And this public lecture fits within our framework of what we call influence, and that is translating important scientific discoveries for a wide audience to inform policy, both here and around the globe. So today we are very fortunate to have Dr. Joachim Knebel here from the Karlsruhe Institute of Technology in Germany to speak here regarding his perspective on energy for Germany and Europe. And I will now just briefly introduce Dr. Knebel. Joachim Knebel is the Chief Science Officer at Karlsruhe Institute of Technology. He is responsible for research programs that currently include storage and cross-linked infrastructures, fusion research, nuclear safety research, and within the German Helmholtz Association of National Research Centers, he is the spokesperson for Nuclear Safety Research Program and for the cross-program activity on electromobility. Joachim has a PhD in mechanical engineering and has authored or co-authored over 100 scientific publications and has given over 80 invited lectures at conferences, public hearings, press events, and specialist meetings worldwide. In 2011, he was awarded the European Science Culture Award of the European Foundation for Culture Pro Europa for merits in partitioning and transmutation research. Following Joachim's lecture, that we are pleased to present a complimentary reception just located outside of the data center, and we hope that you will join us there. And now I would just ask you to please join me in welcoming Dr. Joachim Knebel. Thank you.
Yeah, thank you, Tracy, for this very warm welcome. So I really feel very at home here in Canada. So the first time was just earlier this year, and then we thought it's a good idea to come back and talk a bit more in depth about our energy research and possible joint topics. So I'm pleased to give you a brief idea of what the energy policy in Germany is like, what research is needed to make this new energy policy real, and then also give a brief outline on how this fits in Europe. So, but before I would like to talk about the Karlsruhe Institute of Technology, that not all of you may know, but that is also a nice place to go. Then I talk about the German Energiewende, energy turnaround. Maybe this in 10 years will be a word like the kindergarten or the eigenvalue. We'll see. Then I talk about some selected research issues. So this is not comprehensive. That's just a little glimpse, and whatever additional questions you have, I may have some slides to talk about this, and then let's see how much time I have left for the energy perspectives for Europe. So where do we come from, the Karlsruhe Institute of Technology? So it's two lines. It's the former National Nuclear Research Center, founded 1956, and the oldest technical university in Germany, founded 1825. So we changed our names from time to time, but today we are the Karlsruhe Institute of Technology. It's a state university that mainly does the teaching, but closely combined with research. And this gives the link to the National Research Center, where we do national provident research within the National Helmholtz Association that has more than 24,000 scientists. So some numbers. We have not as many students as you have, but nearly 24,000. We have nearly 9,000 employees and 373 professors. So a nice number. And our major emphasis is on the three pillars, being research, being teaching, and innovation. Because if you want to do higher education, you have to be at the forefront of research, and you have to be in close collaboration, in close connection with industry to bring your research ideas in the market, or to get influences from the market, from the industry, that feed back in the education of the young people. So this triangle is very important for us. And after this merger to this one new entity, KIT, it was quite difficult to define the major research topics, the major research fields. But now we decided it's energy, it's environment, something that we call future technologies. For example, all the automobile systems, electromobility is in there. It's fundamental questions. So, for example, we have a huge experiment to measure the mass of a neutrino, which is essential for fundamental sciences and to understand the Earth, the world, the universe. And then something very important for us, what we call society and technology. Let's just say we link the social sciences, the humanics, with the natural sciences and the engineering sciences. So we have a small faculty for humanics, and this is very important if you do new inventions and to bring these inventions in the market. So energy turnaround, a few slides. Why do we always talk about this? Well, of course, 2011, there was the Fukushima accident that really changed the mind of the people in Germany. There was an immediate shutdown of the older nuclear power plants. There were the stress tests. There was what we call an ethics commission with many parts of society, of politics, NGOs, nominated by our Chancellor Angela Merkel. And then it was decided in the year 2011 that we even faster phase out of nuclear and go towards the renewables, the energy efficiency, because of this accident in Fukushima. So we had, this was not a new policy. We had this long ago. It was just accelerated, this phase out and the turn towards renewables. And if you compare, you don't have to read all of this. If you compare Europe and Germany, then the keywords decarbonization, reduction of greenhouse gases, renewable energies shall be the central pillar for future energy supply. It's more or less the same. And when you look at the energy, the electricity target from renewables in Europe and in Germany, it's more or less the same numbers. So 1/3 in 2010 or between 60, 80, 90% in 2050. So there is no real difference. It's just the difference that Europe goes with nuclear and Germany goes without nuclear. And now there's the question, how can we do this? How can Germany develop to one of the most energy efficient and environmentally friendly economies worldwide? So, as I said, we call this Energiewende or new energy era. And the transformation processes, the restructuring of the energy system is quite ambitious. So if you look at the numbers, and they were already set in 2010, so Fukushima just put more emphasis on it, is that the greenhouse gases shall be cut by 80% by 2050, that we intend to go to a huge share of renewables in our energy supply, the whole primary energy consumption shall be reduced by 50%, and so on. Some very ambitious goals. And in order to reach them, the government introduced in summer 2011 an energy package. And with energy package, we mean laws. You don't have to go through them. It's just when you look at it maybe later on. It's a set of laws that, for example, give the legal framework for the promotion of electricity generation from renewable energy sources. So this EEG law, I come back to this later. It's measures to accelerate the expansion of the electricity grid, which is extremely important if you have the renewables inside. So all these acts are now online and help to do this energy turnaround. And if you look at the now electricity side, for example, 28, we had 636 terawatt hours electricity consumption in Germany. This was from renewable energies. That's all the rest. And what the concept for 2050 is now, that we just reduce our electricity consumption by 25% by efficiency increases. We import a certain amount of electricity from our neighbors, and from the rest, there 80% shall be from renewables. That's to say, by 2050, we intend to decrease our electricity production in Germany by 50%. And this sounds kind of feasible to increase from, at this time, 14% to 80% in 2050. And if we look today, 2012, already do we have 25% of renewable energies in the market. Still, there is a large share of natural gas, that's lignite, that's bituminous coal, that's nuclear, and that's gas. And the real challenge is to go here to zero and to dramatically reduce the coal consumption. And how shall we do this? In an interim time, of course, because the nuclear goes from the grid, we do need new coal-fired plants, because somehow you have to make up for the baseload until the renewables, for example, the large wind farms or the biomass technologies come into the market, are hooked onto the grid, are combined with pumped storage hydropower plants, or what is very important, are combined with new storage technologies. Because as wind and photovoltaics are fluctuating, this is the real issue. How can we store the electricity chemically, electrochemically, as pumped water? How can we modify our grid? And in general, when you not only look at electricity, but on energy in general, how can we modernize our buildings? And these two slides, they come back again and again when I go on each of these examples and give the view of a researcher on this. So the major new issue of what happens in Germany is that we, in the future, will no longer have these point-wise huge power plants like nuclear plants or several coal-fired plants, one beside the other, but decentralized, smaller electricity producers. So we go from point to area. We go from central to decentralized energy production, but also the consumption most probably will have to change. So we, the people, the industry will have to change from the direct consumption to storage. So the consumer attitude, maybe also the industry attitude, will have to change and will have to follow the energy offers. And the consumer actively will control and provide energy services by being a shareholder of wind parks or having its own photovoltaics on the roof, from which he uses the electricity himself or stores it himself or sells it to the market. But just to give you a few numbers as an idea, so the annual peak load electricity in Germany is 80 gigawatt, so 80 huge coal-fired plants or some 60 nuclear power plants as an equivalent. So the installed electricity capacity right now is 160 gigawatt, and the reliably available capacity is 93. So that's what we for sure have whenever we need it. But out of this, only 12 gigawatt is from renewable energies, mostly flowing water or pumped water, and just a little bit of wind. And the difficulty, of course, you know this, is if you look at these annual full load hours, then the difficulty is with the wind, with the photovoltaics. It's just too little to make up for base load, and that's why modified grids, smart grids, as we talked the last few days, also with this meeting in Toronto, or the storage is important. And just to give you an idea on what this looks like in Germany. So this is from the stock exchange, the electricity stock exchange, from January 2010 here to February 2013. So for all of Germany, the wind energy that is fed into the grid. So this is the installed power, of course, increasing due to the new builds. And these are the peaks of wind delivered to the grid. And this Renewable Energy Act says that the grid must take and must pay for the electricity and all the other, the renewable electricity and all the other power plants have to do load following behavior. And for example, here in 2012, the minimum was 135 megawatt. The maximum was 24,000 megawatt. So just see how the grid has to react if these huge spikes are there. And the same, of course, is true for solar. So here we have now more than 30 gigawatt installed. But, well, if there's no sun, there's no electricity. But still, there's even one spike where we had 27 gigawatt out of 28 gigawatt installed. So if there's a sunny day, then there's really a lot of energy going to the grid that has to be taken up by it and paid for. And if you add now wind and sun, then this looks a bit more even, but still that's a real challenge for the grid and for the storage. It's also a challenge for the price. So here's given the electricity tariff for private households between 98 and 2011. So the last two numbers I don't have here. And what you see is that the gray bar, the generation and distribution, is more or less, well, there was a ditch, but it's more or less the same than in 98, but the taxes dramatically increased. So we have an increase of 50% of the tax, an increase of 170% of the taxes. Half of the electricity price that we pay today is electricity. And the Renewable Energy Act, of course, also makes up for some part of this tax. So this, the consumer has to understand and to pay in the end. And just for the renewables, it's 5 euro cent per kilowatt hour. And the questions that for sure you have, that everybody has, is the public willing to pay for this energy turnaround? Are we willing to change our habits to make up for this change from the point-wise to the distributed production? What's about the security of supply or the competitiveness of Germany, of our industry? What do our European neighbors think about it? Because sometimes they get electricity more or less for free. These are the negative electricity prices when we give electricity and money because we cannot use it. And can research provide innovative solutions? And this now brings me to the second part, some issues. And when we look at KIT, at our major energy focus, then it's on energy efficiency, on the storage networks and systems, and on renewable energies. And some ideas about large wind parks. For example, the local utility, the EnBW in the southwest of Germany, they erect huge wind parks that are between 16 and 32 kilometers outside in the Baltic Sea or in the North Sea. So the future planning is up to nearly 100 kilometers outside. The water depth is up to 40 meters, so it's comparable to your lake. You could do similar things here offshore. And the range is here, the first one is 50 megawatt electric, the next nearly 300 megawatt, but it goes then in the gigawatt range. The difficulty with the wind, even for the offshore wind, is that the availability, the time availability over the various years really changes between 25% and 15%. So the more you build, of course, the more electricity you get. But if there is a year with little wind, then the absolute amount is low. So you must do something about storage, or you have to go to bigger turbines. And one means to go to bigger turbines is just to make them larger. But the weight is so huge that the cranes, the boats that you use to erect them offshore, you cannot make them larger anymore. So technically, it's probably no longer reasonable and feasible. And that's why we go to superconducting lightweight generators. So here's a little sketch of it. So we have a huge technology in high temperature superconductors, and this makes them much lighter. Of course, you have to put a cryogenic technology to it. You have to cool it with liquid nitrogen. And we are now about to build one prototype in a European project. So the project is called Superpower. And what you can see is that you really go down with the weight of the turbine, but you can increase the power up to 10 megawatt and maybe reduce the weight by 30–40%. So this would enable us to build huger wind power plants offshore in order to catch more energy from the wind. The energy goes with the third power of the wind velocity, and that's why larger wind turbines are better there. But still, when you have these huge wind parks offshore, you have to bring the electricity to the grid, and we don't have to read through all of it. Joachim, we talked about this yesterday. It's this new superconducting cable technology where the three phases are concentric, one in the other, so that the field outside is more or less zero. So this is now a 1 kilometer high temperature superconducting cable of this BSCCO technology for 23 megawatt power. So it's a demonstrator that will go online next year in the city of Essen, so between two transformator stations. And the advantage is that you gain a lot of room in the cities, that it doesn't disturb the public. And I'm quite sure it will be a real event when we take this in operation. And yesterday we talked about it. Well, why not do it in Toronto? Just a masterpiece there. We are ready to provide the technology. And you anyway have a big ditch along the coastline. You could use it. Or one could use it in combination with the Desertec project. You for sure have heard about it. It's this idea to produce photovoltaics, wind, electricity in the north of Africa. And some percent, 15–20% of this electricity could be transported to Central Europe. But these several thousand kilometers, there you would need these superconducting DC power lines, and these you could do in superconductivity manner. Biomass technologies, something that is important in Germany. We figured out that with the straw, with the wood, all these biomasses that we don't need, if we were to use all of this, we could make up for 15% of our gasoline with this technology. And the basic idea is that in the first step, we take the hay, the straw, whatever, that has a very low energy density, and we do a fast pyrolysis, which produces what we call biolic syncrude oil. So it smells a bit like when you do fish in an oven. But it has a much higher energy density, and this syncrude, this oil-like stuff, you can then transport from these decentralized pyrolysis plant to a centralized gasification fuel production plant. And what you get there is synthetic fuel of the second generation. We work also on the third generation, which has an extremely high energy density, which can be used for very fine car engines or even for airplanes. And that's typical now for the national research side of the KIT, where we have this Biolik prototype plant that has a total investment of 60 million euro, where it's a real large-scale demonstration of it. But we don't only do the large-scale demonstration, we also do the research with it. And for example, young people who want to do some internship or some practical work, they are all welcome here to do 1, 2, 3 months work at this facility, for example. The other issue is the pump storage hydro water plants. There, Maybe you know this, that's the Schluchsee in the Black Forest, southwest of Germany, a very nice area. People got used to it because it's there since long. But if we now think in the future, and if we think that in 2030 we would like to use 30% of the electricity by pumped water storage energy, this would mean 3,000 gigawatt hours that we would have to store if there is 1 week without wind. And if you just do this simple calculation and see that today we have 40 gigawatt hours storage capacity of pumped water, just to make up for this 1 week without wind, we would need 70 times as many storage reservoirs, new storage reservoirs in Germany, which most probably is not possible, or is a real challenge to also get the public acceptance for. One thing that we could do with the storage is not as pumped water, but also as, for example, hydrogen. We talked about this with the SEN conference, to store it in a chemical form. If we do it with excess renewable energies that we cannot use otherwise, then for sure it's a good idea to do the electrolysis, where you lose some efficiency, where you have to transport it, you have to liquefy it, you have to change it. And so in the end, the liquid hydrogen of course loses a lot of its initial renewable energy that comes from the PV cells or the wind farms. But anyway, I think it's much better to store it in hydrogen than to put it in the grid where one cannot use it. Or one can do this power-to-fuel technology with the gas companies. Yesterday, the day before, we talked about it. So with the electrolysis or the reversed water gas shift reaction, you then can do various things. For example, diesel or kerosene via Fischer-Tropsch synthesis, or gasoline, or you can do new oxygenates or methane. So there are many possibilities to convert the excess wind or PV energy via electrolysis and hydrogen to other chemical fuels. It's just a question on how it would be realized. Another issue, new storage technologies, that's, I think, the real issue besides the hydropower plants. And there we have a project that is called Competency. So there are many institutes from the university side, from the research center side, go together to develop new storage technologies and improve existing technologies. And this is the example for the improvement of existing silicium oxide batteries. So where you start with the anode materials, with cathode materials, with the development and investigation of electrolytes. It's the whole process of the coating, so the formation of the anode and cathode material here on the substrates. You have to assemble the whole cell together. And then in the end, you have to form the battery, and we do this on an industrial scale. That's to say, we start from the very fundamentals. We investigate which anode material has to be treated in which way, how has it to be dried to make good electrodes, how has it to be assembled. And then in the end, starting from the material, from the cell, via the battery, in the end we go to a full powertrain system that can be implemented in electric cars. And the objective that we have is these 250 euro per kilowatt hour at a price at 250 watt hours per kilogram. So this is really ambitious if you go on the whole battery system. So on the whole instrument that then finally goes in the car or in a stationary application. and that you can see that it really works. Here you have one of these pouch cells that has 20 ampere hours, and we compared them to other cells, and as you can see, after some 650 cycles, then it degrades by just, no, here, these hours, sorry. It just degrades by 3%. So it's really good if you compare it with other really high-level batteries. And now our latest success was with the International Motor Show, the IAA in Frankfurt. There we had an electric bus that is fully electric driven with our own battery systems. But still, or you have heard that in Germany we want to have 1 million full electric vehicles. And if you take each of them with a 20 kilowatt hour battery storage, if you consider that some of them are running on the street, some of them are empty, so with these boundary conditions, then these 1 million cars in general just make up for 7 gigawatt hours capacity. So 7 gigawatt hours capacity compared to the existing 40 gigawatt hour of pumped storage is little. And if you compare this to 1 hour of wind, then it's even minor. So you see there are huge steps still to go. It's feasible, but it's not simple. This, for sure, you have seen. We also discussed it with the SEN meeting. You have to link various users, energy sources, and storage systems together. There are these smart home technologies that we have, where we, for example, use the cars as storage. So it's that PV cells bring the electricity in the car and the other way around, which is not normal. Yeah, okay, so there I come to the electricity grid. And when you look at Germany, there we have the extra high voltage transmission grid, some 35,000 kilometers, and then the distribution grid has 3 different voltage levels and really huge distances, probably much less than you in Canada, because you have to go over all the continent. But the thing is, these lines, they're only one-way lines. So mostly from the producer to the consumer, it's not foreseen that you have storages in between. And if you look here, for example, at the net power output over the different electricity producers, then you can see that here hard coal, lignite, nuclear, they all feed here in the transmission grid. So that's the dark blue, and hardly any of them go in the distribution grid. So that's what you expect. The big power suppliers go in the huge transmission grids. The wind power here goes all in the distribution grid, and this makes the difficulty if you have really a lot of wind in the north of Germany with the huge wind parks, offshore or onshore, but the electricity, the industry is needed in the southwest, in the south of Germany, then this must be changed. So there must be new extra high power transmission lines built, and that's given by this picture of Germany. So the wind mostly is produced here in the north, and the electricity is needed here in the west, in the southwest, where there are also many nuclear power plants that will go from the grid that you have to substitute. And that's why most of the power lines that you see here in various colors go from north to south. But if you see which one are in the planning phase or which are really under construction or already implemented, then you see that many of these projects are delayed because it just takes too long for the licensing, too long for the discussion with the people, with the communities, which is extremely important. So there is some 1,000 kilometers of extra high voltage lines that are required, so you can discuss whether it's 4,000 or 2,000. But for sure, it's much more than the 200 that we have just yet built in the recent years. And there's really a lot to do to convince the people to have this. So I go over these pictures. That's how we think it could be. It's this research center informatics that you saw also in Karlsruhe, Joachim. The idea between the extra high voltage and the low voltage lines, but maybe it takes too long to explain. The idea is, and that's what we do on the university side, we try to simulate these smart grids technologies on a home level. So what we call our smart home on the university campus where 2 people can live, or on a smart building level where we have a research office building of 3 floors that is equipped with this smart technology. And there we really, with the real components, look into load flexibility, virtual storage, this load shaping, load shifting, together with real pricing signals from the utility. And just to give you an idea of what this smart home looks like, so here are some pictures of the interior. 2 people can live here. All the technology, the equipment is in another room. So we have intelligent kitchen appliances. We have cooling, combined heating and power system. We have an air conditioning that can heat and cool with solar converters, a smart car that can charge and discharge the electricity. And then, of course, we have electric heaters. The people who live there have an energy management panel where they can very exactly see where they use which electricity and how much this costs. And of course, there's an energy management system which helps to improve the energy efficiency in this house. And from this 2-people household, we also go to this, what we call House of Living Labs of the Research Center Informatics, FZI. So that's a building where we have combined all of these components. So we also have hot water tanks or chillers for the air conditioning, this combined heat and power. But it's really all linked together, and you can see how this operates, at least on the size of a building where, I don't know how many people work there, 80, 100?
This building about 40.
Yeah, 40 people, okay. Now, very briefly, and then come to the end. Of course, we also do nuclear safety research. This is also important for a country that phases out of nuclear, because until 2022, we do have the nuclear power. We have to make sure these reactors are safe, our reactors and reactors outside. We have to care for the nuclear waste, for radiation protection, and we, for example, also just have a new professorship for nuclear decommissioning technologies, because we have to accompany the utilities, the government, to do so. So that's an important program that we have. On the other side, we also have a fusion program where we are the technology leader for all the technologies that you need to realize the ITER fusion plant in Karlsruhe in France, or the Wendelstein 7X project that we built in Germany, so a small fusion machine. And just to give you an idea of what this machine looks like, so this was 1 year ago where this torus was assembled. So it's in the north of Germany and is operated by the Planck Institute for Plasma Physics. And I don't know where there's a person. So this is roughly the height of a person, just to give you an idea of how large this machine is. And Karlsruhe, when you look at the international thermal experimental reactor ITER that is being built in France, there we develop and build and provide all the major components that are needed here. So for example, here the gyrotrons, or all the magnetic cabling, and this brought us to the superconducting cables in civil applications, or the tritium fuel cycle, the blanket modules that you need to keep the plasma shut in the vacuum. Now some last slides for the Europe energy perspectives. Europe is rather heterogeneous, so many countries have many energy directions. And in order to bring these together, in order to bring academia, research, and industry together, the European Commission thought of an instrument that is called European Institute of Technology, the EIT. And within this EIT, specific topics are addressed in what we call knowledge and innovation communities, so these KICs. And one topic that should be addressed is energy, and there were several consortia applying for this big project. And the project that was led by Karlsruhe and that has the name InnoEnergy, in the end was the winner for this energy concept. Most probably, I think it was the winner because it really combined all the energy sources, from the renewables to coal up to nuclear, which is a topic in Europe. So we did win this KIC InnoEnergy. It's a project of some 150 million budget per year that is distributed to bring the technologies in the market finally. And if you look on how many partners are in there from industry, research centers, and universities, so there's 165. It's quite a large amount. And the topics that we are addressing here is, from the German side, we coordinate the energy from chemical fuels. So this Biolic plant is a major component here. Clean coal technologies are coordinated by Poland. The smart grid idea comes from Scandinavia. The Iberian, so Portugal and Spain, they look on the solar photovoltaics, and France combines nuclear with renewables. So it's really a mix of all the energy technologies in the triangle that you have research and technology combined with education, and this know-how you finally bring to an innovation, to the market, to the industry, and that's what this KIC is funding. And KIT is the coordinator of this. And maybe if you look at Europe, the picture that I showed for Germany looks different. So for sure there will be an increasing amount of renewables. There still are fossil fuels. Probably they will be reduced in favor of the renewables. But when you look at Europe, for sure nuclear is an issue. There are new power plants being built in Finland and in France. And we just see what the future brings us. And then, to be in time, the final remarks. I think the energy turnaround, this new energy era, is really a long, challenging journey. Whatever I showed you, whatever would be implemented in the market, for sure is not free, is not cheap. There must be some smart ideas in order to implement the renewables, because just building photovoltaics or wind farms doesn't help a lot. You need the public acceptance to pay higher prices or to go to new infrastructures. We, from the research side, are ready to do the research, the education, the teaching. We are ready to do it with partners. That's why we are here. I think it's a good idea to also exchange people, that you look over your over the borders of your own country, get ideas from other countries, and maybe implement it at home. That's this idea. It's not a national issue, the energy. It's for sure a global issue. And the more we work together and exchange ideas, the better it is. Because I said this on Monday as well, politicians must take decisions. That's important. They should stick to them and bring them to a good end. But they will not be able to bend physics or market laws. That's just set. Okay, thanks a lot. I think this brings me to the end.
Thank you, Dr. Knebel. We have time for a few questions.
So
So one effect of the variability in solar and wind has been the temporary increase, I guess, in the consumption of coal. And coal plants, as you mentioned, you said it's temporary, but what is the, when is the dependence on coal plants going to decrease? Because in fact, the carbon footprint of Germany has increased in the last 2 years.
Yeah. So at present, we calculated the need for 17 gigawatt coal required to make up for the nuclear power plants. Until we have storage capacities or better grids or smart load shifting capabilities to be able to do without the coal. And if you look at the coal-fired plant when you erect it now, there are several brown coal plants being put on the grid right now, then they have a lifetime of 40 years. And I would presume they run for these 40 years till they come on their normal end of life. And at this time, I'm sure we have better technologies for the storage or the smarter usage of electricity that we gained a lot in energy efficiency. It's not only electricity, it's energy in general, heating as well. In Germany, we heat a lot with gas or oil, but there's an increasing number also of heat pump systems for the houses. So this electricity also should come from renewable energies. And there, I think you have to align the operation of your heat pumps for house heating with the production of renewables, which is not the case right now. So for example, with my home, whenever I use my heat pump, I pay the same price Monday to Sunday. And this for sure is not reasonable.
So if I can understand, if I can clarify, so does that mean that you expect that the carbon footprint will be higher for the next 40 years?
If there is not a dramatic reduction in the total energy consumption, yes. Because the nuclear goes from the grid, coals go on the grid, and the renewables are not baseload capable.
Laura?
Yes.
Thank you very much for a very nice talk. I'm just wondering about the issue of fossil fuels. Like in North America, people, like in US, they have lots of this shale gas.
Yes.
So in Europe or in Germany, are people exploiting that? Do you find any new shale gas resources? Because this will decrease the carbon, CO2 footprint a lot.
So the shale gas discussion in North America completely changed the energy landscape worldwide, and the price system shifted. So gas is extremely cheap. We very closely watch this development in Germany at KIT. We have professors who also look into this technology, so to make it as clean as possible. But there's a strong public discussion on the environmental issues of this shale gas technology. So there's really the question whether this should be or could be done in Germany or not. It's not yet decided. There are sites that are good for shale gas production in Europe, but it's not yet decided whether they will be exploited or not, at least not in Germany.
So what about the other European? I know England, they're also talking about that now in UK.
Yeah, I don't know. I cannot give you. Yeah, I cannot give you a good answer on this. Sorry. Yes.
I have two questions, but they're related. So first, if you can comment on in Germany, the social environment for the siting of transmission lines, which would be required because power is being used in the north, no demand is somewhere else, and it's always very difficult. We found in Canada and Ontario to build transmission lines. It takes a very, very long time. So if you can comment on that. My linked question to this is, you raised the issue of storage, which is clear because of the renewable generation. And one option that we think about to study here fairly closely is the idea that an interconnected grid, through interconnections into other markets, into other sort of provide kind of, maybe it's not the right word, but de facto storage, in the sense that you use attributes of base load and other sorts of generation on a larger grid,
Yeah.
through interconnection that obviate the need for, and then you can do seasonal and direct
Yes.
arbitrage of electricity prices and so on. Any comments on that?
Yeah, yeah. So as for the grid, there is this law for the acceleration of the expansion. There's a clear roadmap on how a map for all of Germany is done with indications in which corridors there should be the extra high power line. So this is done. This is public. This was debated. Everybody can comment on it and bring in his objections. Then it goes the next step, that it's discussed in more detail, that it's really specified where the power lines are to come. Then the public is consulted again. The communities are consulted. So there's a strict roadmap on how to realize finally the power lines I showed to you, always with the discussion with the public, but in defined timelines and with defined courts that can be appealed when there's a dispute between public or communities and the companies that intend to build the power lines there. So the law shall really accelerate it from what it takes today, 10, 12 years, down to 4 or 5 years. But the difficult thing and the important thing is to have the communication with the public, to educate them, to make them understand that this is required if we want to go for this Energiewende. And the second thing was with the grids and the interconnection with other countries. That's about to be developed. It's, for example, if you take Poland, some of the wind energy was guided through Poland, which puzzled their grid quite a lot because it was just too much power. So there, for sure, the control mechanism have to be much more improved, which is on a state-to-state level, so that you don't hinder excess wind electricity from Germany to go in another country. But Germany should also not press the other countries too much on taking the excess electricity that we don't need. And this is seen, so maybe also this Renewable Energy Act has to be adapted in the way that when there's really too much renewable energy that cannot be used directly, that cannot be stored or cannot be transferred to hydrogen or natural gas, then maybe one just should cut off the wind park. Yes?
I have a question regarding the power to gas we were talking about.
Yeah.
So I understand that when there is a lot of excess of power, you have more resources to do something with it, it's better to do something
Yeah.
with everything. But what is the efficiency when you go from wind to gas and back from gas to power?
It's a question whether you go, I don't know these numbers exactly by heart, but if you go to the hydrogen, one can feed it in the national gas grid, which is huge, which is enormous, and you can between 2 and 5% of hydrogen. That's the best thing you could do. Why go back to the electricity in the first place? Well, you could do it, of course, but
Because it's a way to store, right? It's another way to store. And I'm wondering if it is a possible way to store, which is comparable to other storage technology.
I would prefer to put the hydrogen in the gas grid or to transfer it to CH4 and then put it in the grid, because then you don't lose that much from the efficiency.
It still acts as a storage, but you're not converting it.
No, I understand, but the fact is if you did wind to start with, it's because you wanted power.
Yeah.
It's not, I mean, if you wanted gas, you...
So you said we started with the wind because we wanted power.
Yeah.
Because that's the easiest thing you get out of a wind machine. So I think in the end that the market has to organize it.
Question, Dr. Joachim?
Yeah, just to follow the previous question. So is there some like analysis based on exergy available if you look at the power to fuel, then like a fuel to power cycle? So especially for the hydrogen you mentioned, basically only 20% energy is going to hydrogen, right?
Yes. Yeah. Yeah.
Then
Yeah.
you're going to kind of put hydrogen with natural gas, then kind of combust it. Then you are going to generate electricity. So that's kind of efficiency about 30 to 40%. So that's kind of, so
or we use it for heating in the houses. If you argue with the efficiency of the total chain, then you are lost because there's hardly any efficiency left. But as the electricity is produced anyway, and as maybe if you don't force all the other power plants to ramp up and down when a wind farm is with 17 gigawatt and then the next day it's down to 0 because there's no wind. I mean, this is also not good for the normal coal-fired plants to always go up to 100%, go down to 40 and so on. Maybe then to have an electrolyzer running in parallel is better if you look at it from the point of view of the lifetime of each of these plants. So if you only look at the efficiency of this one line, power to gas and then back to electricity, this for sure is not the way that you do in the first place. But if you have the excess electricity anyway, then you could store it this way. So it's not simple to argue in this way, I fully agree.
I was not, in fact, I was arguing in favor of that because, as you say, this wind is there. So it's better even if the efficiency...
Yes, to use it this way, yes,
it's
okay.
not that bad.
Yeah, maybe then I misunderstood you.
No,
Yeah.
no, in fact, no. I
Yeah.
just wanted a number, otherwise I think it's not that bad. It's not that bad.
We have a
Yeah.
question here from Patrick.
Yes, and this is a question from a chemist who is trying to ask a public policy question, so you might be misguided. But where does the non-legacy world fit into this whole picture? Meaning third world countries, emerging countries that are largely populated, but probably not able to finance all of these changes. So there is this whole school of thought, at least in the sort of chemistry-related community, of decreasing the importance of the grids through personalized energy, which is similar to something that you showed, where each, say, a house will, convert at least to a solar means energy, store it to, say, water splitting, hydrogen storage, reuse it, but essentially, minimize this whole grid approach to the problem. Is that something that is being considered at least for certain parts of the world where investment in a grid and these large-scale investments are maybe just not even possible yet?
I think that there we have the good example from Waterloo University, where you do this on a watt or kilowatt scale for remote areas where you use the simplest technology, PV technology or simple batteries to store the electricity that a small village can live of it. So I had some slides where we, for example, used these lithium-ion batteries I showed, these battery blocks, in combination with photovoltaic panels on islands. So there will be an island in Greece where we demonstrate this so that it can be completely autark with a system as simple as possible.
Right.
So whether this is possible for an industry campus,
Right.
I don't know. You would have to see how expensive the upscaling is in the end, because the price is extremely high right now. But just wait 10 more years. I'm sure if the technology develops, then the price goes down.
Right, because that's kind of self-sufficiency instead of this grid
Yeah.
approach, I guess.
Yeah.
Okay. If no one has any further questions, I have one further question, and that was the last one. A clarification on the 50%. So we have 50% consumption reduction by the year 2050.
Yeah.
Is it acceptable to Germany to meet most of that or all of that via production through jurisdictions or neighboring.
So that's the global objective of Germany, and I'm quite convinced that the people will follow this. The incentives to do so should be better visible. At least to me personally, I think one should really see it on the bill from the electricity or the gas company, that if you use less electricity or gas, that in the end you also pay less. This is not fully aligned right now because all the investments and maybe these laws that we started 10 years ago have effects today that we didn't foresee 10 years ago. So there must be changes. But if the people notice that it's a benefit for them and that it's good for the country or the nature or the whole globe, then I think we also would accept to change our habits and maybe in the long run don't pay more for it.
Is it going to ask a follow-up?
Sure.
It's just one problem that we see here is that the electricity companies, the local distribution companies, will be people billing the end customers, make more money when people use more energy, more electricity.
But this must change. This must change.
Right. It's not in their interest to reduce consumption because they make less money and they make a fixed rate of return profit on that. So the policy and system is set up here, and also in the United States, for example, where there's no reason for you to ask people to use less. You make it a smaller bonus.
Yeah, but unless we don't change this behavior, we will not succeed. And I think there's a good mental approach in Germany to go this way. Yes, please. Final question.
One of the things that frustrates us in Ontario is the inability to obtain smart metering data for research. But of course, if you want to change people's habits, one possible way to do that is to do some analysis on the data and show them how they could save electricity or how they rank compared to similar households. So I was wondering if there are similar problems in Germany, or is it easier to obtain
it's this
data for research?
privacy issue. You really have to secure to lock these data. What we did in this smart house, just with 2 people, was to have a kind of competition who uses less electricity in total. One could do this if you do smart metering, chemical faculty against mechanical engineering faculty. So you have the smart metering in their buildings, in the lab offices, so you have to normalize it in some way, and then you see who is better. Just give a kind of competition. And then I'm sure if you can say, well, normally you say, my bicycle is lighter than yours, mine's only 5 kilograms, and then that's good. But then you can say, I don't use 3,000 kilowatt hours a year, I just have 2,500. I think you have to go in this way. Everybody shows its brand new smartphone and is proud of it. Why not show on the smartphone how little electricity used just today?
Is the issue of privacy and smart meter data access as important in Germany as it's beginning to be?
I don't know with the private people, but I think when you then go on the grid level, you really have to make sure that nobody can interfere there and do any damage to the grid management in total. Well, many people give their data to Facebook and these things. Maybe people are more relaxed. I don't know.
All right. Actually, I would just like, if anyone else has any additional questions, we are pleased to offer a complimentary reception, and Dr. Joachim will be available then for questions. So thank you very much.
Yeah,
Dr.
thanks a lot. It was my pleasure.